Let's continue to look at conservation of momentum in 2 dimensions. Now, as I go through this video, I'm going to not take pauses as much as I would during a class, so you may want to pause the video from time to time to copy down the problems and copy down what I'm doing. So 2 zombie heads of unequal mass are on an ice rink. And if you don't like zombie heads, make them something different. I kind of did this. I think I made this slide back when The Walking Dead was really a huge deal. So the first one is 4 kilograms going towards the second one, which is 2. So initially, there's only momentum in the x direction. That's it. Nothing's moving in the y direction, and the 2 kilogram one is stationary. And then they move off at both at angles of 35 degrees, and we want their final speed. So we'd call this, maybe we'll just call this V2 and V4. So definitely we can see there's going to be some trig involved like in previous problems. First thing we want to look at is the x-coordinate. And remember, momentum's always conserved, so momentum in the x direction would have to be m1 v1 plus m2 v2 equals m2 v2, or m1 v1 plus m2 v2 afterwards, initial and final. Write that in there. So when I start to write these in, it was 4 kilograms, I'm moving at 4 meters per second, and then afterwards, now remember, momentum is mass times velocity. I believe the 2 went up, so this would be 2 times v. This will be 4 times v. So the x component will be 2, or I called it 2. That's why I said, and I called this 4. 2v2 cosine of the 35 degrees. And it'll be similar for this one. 4v4 cosine 35 degrees. Now at this point it's just a little bit of algebra. And luckily cosine 35, we all have calculators. We can calculate what that is. Back in the day we had to look it up on charts if you didn't have a calculator. So let's see, 16 is 3.28 v4, 1.64 v2. And then I divided both sides by the 1.64. I have to do that to all the terms. Because then things get a little bit simpler. 9.78 is 2v4 plus v2. But we're not out of the woods yet because we have 2 variables. So we have to figure out the y-coordinate. What's nice in the y direction is it was 0 initially because nothing was moving vertically. It was only moving horizontally. So instead of using cosines, we're going to be using sines because we're going to be finding the opposite, the side of the triangle that's opposite the angle. So this will be, for example, 2v2. This is the momentum. Sine of 35 degrees. An important thing to remember about the 4 is it's going to the right, but down. It's going over and down. That's why that's negative. So at this point, it's really just some math. We can figure out what the sine of 35 degrees is and double it, and then multiply by 4 for the second one. Now what I did was I moved the v2 over, and I divided everything by 1.15. And 0 divided by 1.15 is 0. Oh, that's a nice result there. v2 is 2 times v4. It's nice when things work out evenly. So now I have 2 equations. I took this equation and I substituted. This was v2, but now I've substituted and I've made it 2v4. Then it's really easy. 9.76 is 4v4, and divide by 4. And then I know v2 is twice that, so I just had to double it. And that gets our answers. So it looks like the smaller one goes off at a faster speed, and the other one gave up a little bit of its momentum and slowed down. And that kind of makes sense. It would give up a little bit of its momentum to the other one. So again, feel free to stop the video, pause the video whenever you need to. Now let's try another one. So 2 pucks are on an air hockey table, and we're going to have them both moving. We're going to have the red one moving to the right or to the east, and the green one moving to the left, or you could think about it to the west. And they're going to collide with each other and careen off. Maybe you've done this, when you're had a couple of air hockey pucks or something like that and playing around with a friend. So we want the speed and direction of the red puck. Oh, because we know it for the green puck. They tell us for the green puck the speed and the direction. It's 40 degrees to the south there, south of the horizontal, and 1.1 meters per second. Again, with all these two-dimensional problems, we're going to break them down into x and y. We actually could do 3 dimensions too if we wanted to do a z vector, but we're not going to get that complicated. So m1 v1 plus m2 v2, just like we see, law of conservation of momentum. Unfortunately, in this case, both of them were moving. Now, they gave us the masses, I believe, in grams. So that's where I had to convert to kilograms. So the one puck was moving to the right, and that's its momentum. The other puck was moving to the left, and that's its momentum. For the one we don't know, the one that we're not sure about, was the one that went up this way. Remember, momentum is mass times velocity. So its mass was 0.15, its velocity is v. And they didn't tell us the angle. That's okay, we'll find it. So its x component, the momentum in the x component would have to be the mass times the velocity cosine of theta. The other one we knew. The other one, I believe, was the green one we knew was 1.1 meters per second, 40 degrees. But it's going still to the left here, towards the negative, so that's why we're going to subtract it. I tried not to go too fast here. I tried not to, like to take the algebra step by step a little bit. So I added the momenta on the other side, and they become negative. And then I figured out what this is in my calculator. I calculated, there wasn't anything I could do here. That had to stay 0.015 v cosine of theta. Now I'm going to add 0.0169, or 169 there, 0.0169, and then divide by the 0.015 to get to this point. So I took my x momentum as far as I reasonably could. Now for the y coordinate. Initially, they were both moving horizontally. That's good. Makes our lives a little bit easier, because then it'll be 0. Now in the y coordinate, again, we're working all with momentum, so it'll be the mass times the velocity, but it's times sine of theta. And for the other one, it's pointing downwards, so it's mass, velocity, sine of 40 degrees. and I made it negative. You might say, well, why not use maybe negative 40 degrees? There's other ways to do this, or you could start at 0, and let's see, you could say it's 220 degrees. It's easiest, I think, just to subtract, just to keep everything like a small normal triangle and subtract. Now here I didn't show all the steps. As I said, you may want to pause the video and work through it and make sure you can get to this point. So I do have two unknowns and two equations. We've got this equation. I just got an equation here. I'm going to divide the equations. Just like you can add equations and subtract equations, you can divide them. So I put v sine theta is 0.943 over v cosine theta is 0.524, because then the v's cancel. And if you know me, I'm a big fan of sine over cosine because that's tangent. So this ends up being the tangent of theta. I'll show one more step as 0.0943 over 0.0524. And when you divide that, you get 1.8. Then I can take the inverse tangent. It kind of is important to note that it's north of east, because that gives us the bearing. Once we know theta, we can take either of those previous two equations. I used the sine equation. You say, where did I get that? It's just this equation right here. And all I did was substitute. Now it's what? 60.9 or 61 degrees is 0.943. I can get that sine value in the calculator, divide it over, and I get that the final speed is 1.08. Now we should look at these numbers and say, are they reasonable? The 60.9, 61 degrees, that doesn't seem impossible looking at the picture. You say, well, what about that 1.08? Well, the initial velocities were 1 and 1.2. It's kind of in the ballpark. It seems like it's reasonable. If we get 1,000, something's very wrong, and we need to stop and take a look at that. Okay, let's try one more of these. And as I said, I'm going faster than I normally would in a class lecture. So feel free, pause, absorb things. You can even rewatch them, slide the slider back and take another look. So very similarly, we're going to have a 100-kilogram man running east collides with a 56-kilogram man running west. Now, after the collision, the 100-kilogram man, let's see, they tell us is moving at 0.8, 30 degrees north of east. Oh, and we want the speed and the angle. Now, for the 56-kilogram man, that's the one that I have in red on the drawing there. So let's just take a minute and look at our triangles. This momentum will be 100, which is the mass, times the velocity, which is 0.8, so that's 80 kilogram meters per second at 30 degrees. And in a few minutes, we'll break that down. We'll want to do 80 cosine 30 degrees and 80 sine of 30 degrees. The other triangle is going to look a little bit different. Let's see. We don't know its v, person's v. So that's 56. And we don't know the theta, 56 times v. But the x component will be 56v cosine theta. And then this will be the y component, 56v sine of theta. And it will be negative. They'll actually both be negative because the person's moving to the left and down. And hopefully I have the math on the next slide. And I do. So looking at the x-coordinate, law of conservation of momentum, just like we've done before. Be very careful of signs. The 100-kilogram man is moving to the east. 56-kilogram man to the west. It's going to be subtracted. Now, we knew enough information. We knew the angle and the speed for the 100-kilogram man. So I tried not to take things too fast. I did the left side. I did parts of the right side. And luckily, the negative is going to cancel, because I'm going to subtract 69.3 over on both sides. And if you check your algebra, it's actually not that bad. You get V cosine theta is 1.45. Now we'll take a look at the y-coordinate. They were both running horizontally the way we looked at it. So in the y direction, the initial momentum was 0. We had a lot of information for the 100-kilogram man. We knew everything. We knew the velocity. We knew his angle. But we don't know that information for the 56-kilogram man. So V sine theta is 0.714. I bet you can see where we're going to go next. I have two equations. I have this equation and this equation. Maybe we'll circle them. And we're going to divide them. We're going to do sine over cosine, because who wouldn't want to do sine over cosine? And sine over cosine, if you remember your trig identities, is tangent. And then let's see, 714, excuse me, divided by 1.45. It's going to be about 0.5, or pretty close, 0.492. So really close to a half. And just to remind you of the bearing, remember it was down this way, was the way that person was moving. So here's the west, here's the south. So that means we're going towards the south from the west. South of west. It puts us in that third quadrant, as you would remember from algebra. Then once we know that, we can easily substitute. We know the 26.2 degrees. We knew the 0.714. And sine of 26 degrees is just a number in the calculator. Let me see what that is. I'll do a little bit more math with you. 0.442. So I get V times 0.442 is 0.714. Just divide the 0.442 on both sides. 0.442